Okay, good evening everyone, and sorry for the delay. Technical problems and sometimes airplanes cause problems. We have a talk here. I will do the introduction real quick. This is Christine Corbett. She's an MIT student and she does research on artificial intelligence. You all probably have had problems with translation, automatic translation systems, and she will actually tell you a little bit more about that. Welcome.
Can I have your... Oh, here we go. That does indeed work. It wasn't working before. Okay, welcome everyone. Sorry about all the technical problems. They, of course, lost my luggage at the airport, which meant I get to use a fun little Windows laptop here. It's all in German. German's a good language, but I needed the machine translation to help me out with the menus there. So I'm Christine Corbett Moran. I'm from MIT in the US, and I work in the computer science and artificial intelligence lab there. And today I'm going to talk to you about open sourcing machine translation. I'm going to give you a little bit of history of the machine translation movement, tell you where we've been, some different approaches, and I'm specifically going to focus on statistical machine translation and present an open source toolkit that's available now on SourceForge for statistical machine translation called Moses. So let's get started. History of machine translation. It was one of the first applications conceived for computers. IBM exhibited simple word-to-word translation system in as far back as 1954, and we had some early optimism here. It will not be very long before the remaining linguistic problems in machine translation will be solved for a number of important languages. We're still waiting on that, actually. This is 1958. So these early approaches, like a lot of other AI research, MT is actually referred to as an AI complete problem. Like a lot of these other AI complete problems, there was a lot of early optimism that sort of fizzled out. And these early approaches really failed to scale to back up such optimism. And here we have a US government report that was just very, very negative, and kind of quelched any research in the field for almost a decade. So we do not have useful machine translation, and there is no immediate or predictable prospect of useful machine translation. So we're working to change that still today, and machine translation is useful for a number of applications. Here's the State of the Union. There was a resurgence after this negative report. There was a resurgence in the 1980s that was mainly rule-based approaches. So if you have all these PhD linguists writing rules for machine translation systems, you can, for certain language pairs, if you hire a lot of linguists, you can get some pretty good output. The disadvantage is it requires a lot of man hours, lots of researchers, so it's only applicable to people who want to invest a lot of money into a certain language pair. So if you wanted to build a machine translation between Finnish and German, then you're not going to have the money to back that unless you're Bill Gates and for some reason there's a war between Finland and I don't know, Germany or Greece or whatever, then you'll back that. But otherwise, these people who want machine translation systems in other languages are just going to lose out. There was another resurgence in the 1990s. The IBM noisy channel model, and I'll explain this term later, but for now, let it just stick in your mind, paved the way for statistical systems with heavy engineering components, and that's some math I'm going to talk about later. And this is where we're really at today. In 2000, we're kind of merging these two approaches, merging the rule-based approach by automatically generating some rules, incorporating more syntax with the statistical approach that really dominated the 1990s. And we're still working on this today because MT is hard, machine translation is hard. You have all this stuff going on in language, sense, order, tense, idioms, ambiguities, reference. If you're not a native English speaker, I'm probably speaking too fast for you, for example. But all these things going on in language make it hard. And the amount of data required for a good machine translation system that's not manually written by people's data in their head, which is a lot of data as well, it's very, very large. You need words, you need phrases, syntactic information. And in addition, it has to be as consistent and correct as possible, because if you have inconsistencies, you're not going to get a good output there. So that's the state of the union today. And the bar is really high for machine translation systems. As a human, you can be very critical because you're probably better than any machine translation system. I'm going to be honest here, it's going to be in the next 20, 30 years at least, just by the time you're 8 or 9. So the bar is very, very high. You want something that's general purpose, not limited to, say, making a flight, but something that can translate any sort of domain of interaction. You want it to be human quality, just the tiniest thing that's off will really stick in your mind, and automatic, so you don't want to hire all these linguists to generate these systems. The demand is very high for a few language pairs, English to Arabic, or English to Spanish, or between different European Union countries, there's a high demand. But adequate MT for most language pairs, still non-existent. Here's some sample output. I'm not going to read this all here, but you can sort of see the output is right here, and it's adequate. This is one of the better MT systems. Through petition received by the Inter-American Commission on Human Rights here and after on 6 October 1997. So it missed a couple things. This should be hereafter. October 6th, though we can parse that. Maybe we want to switch those two. And petition probably needs an article like the or a or something like that. But you can parse it, so it's getting close. So again, I talked about all these demands for MT. You have the European Union, where in the European Union, it's by law, in the parliament, you have to translate important parliamentary documents between all pairs of official languages of the EU. So if you study complexity theory at all, you add another country, that adds another entire all pairs sort of situation. So that in itself, the EU really invests $1 billion a year, at least, in humans translating. So even MT, if it's not perfect, if it can help a human translator do their job more quickly, get them started, then that's another application. And the US government and military, as well as other militaries, employ scores in intelligence translation. And translation, this is where I'm at right here. Translation renders information a wider net of accessibility. If you have a document that you want to read in German, that you want to read in whatever your native language is, if that document exists, whether it's documenting source code, whether it's your personal blog, whether it's a user manual for something, that should be accessible to anyone, whether or not that's their native language. So one of Google's most important assets is their growing machine translation suites. They use a rule-based system, more of the 1980s approach that's very functional but limited, which is why you don't see all language pairs on Google's translation engines, but they're transitioning to the statistical methods for some of the newer and up-and-coming languages like Arabic and Chinese, and they're using methods very similar to those I'm describing today, but a little bit more closed source and proprietary. So here we go. This is our goal, sort of, to climb this triangle. Here you have foreign words and source words. The easiest approach to translate is just do it word by word. But if you can imagine, I'm sure you've done this with your favorite new language that you're learning, it ends up a little funny. So that doesn't end up quite right. But you can do this in more sophisticated ways and approach it in a statistical method and actually generate some good output. The syntax to syntax, imagine if you've ever done sentence diagramming in school, marking things with verbs and nouns and whether it's a subject or an object. If you were to do that in both languages and then generate automatically or with linguists a few rules to translate one sentence diagram to another sentence diagram, we actually call them trees, but it's the same sort of concept. Then you could really work on this level. This is a little far off, maybe psych or some sort of knowledge semantic database using WordNet or something like that. You could translate semantics meaning. And some approaches actually try an interlingua. They posit that we could use an intermediate language as sort of an interface between all different languages. And then you don't have to do all pairs. In the EU example, you could translate Finnish to the interlingua, and then from the interlingua you'd have a translation to any other language. So that saves a little bit. So this I just went over in that diagram, which was a little more clear, but you can do word-to-word, syntactic, interlingua, and statistical sort of is now incorporating all these, trying to climb this tree, and coming up all the gory details. Much of the state-of-the-art theory was proposed by IBM in the early 90s, and the goal is to find the most probable target sentence given a foreign sentence. So you're going to try to translate from this foreign language to a target language. A lot of the convention in the literature is to call the target language English or E. You can make up something that's not so Anglo-centric, but IBM, I guess, was very interested in translating into English, so most of the time they'll refer to the target language as E and the foreign language as F. Now the basic idea is to use parallel corpora to automatically align words and sentences deriving probabilities. Now what are parallel corpora? If you have two texts that express the same thing, maybe translations of each other, then you can use algorithms to align the sentences. Say this sentence says the same thing as this sentence. And when you have these two sentences that say the same thing, you can derive statistics about that. If you align the words and the phrases, you can say this phrase aligns to this phrase 50% of the time, and this phrase aligns to another phrase the other 50% of the time. And I'll show you a table, that'll probably make more sense. This requires a really large amount of data, which is still viable for a limited number of language pairs. We have this data for the European Union that in their parliamentary sessions, as I mentioned, translate lots of parliamentary documents between all language pairs. So given all this data that's human generated, we can learn from that and then do our own statistically generated machine translations. So here we're going to go. I'm going to go through a bit of math here. This is just to get the symbols a little sticky in your head, and then I'm going to actually go through this in more detail and come back to this slide. So given a foreign sentence F, we're looking for the English sentence or the target language sentence that maximizes the probability of the English sentence given the foreign sentence. That's this notation here. This will give you the English sentence which yields the highest value for this probability. And this is statistically the most likely translation. And hopefully, if you've trained your system well enough, this is the best translation, the most likely best, if you have enough data and very good data. So we can generate this in a sort of easy manner. If we have, this is the table I was mentioning, translation pairs in a parallel corpus. So here I have maybe, what if I have the same children's book in two different languages? In one language, French, it says "Je mis mon chat," or however you say it in the best French accent, which can either translate, in our children's book, it translates two different ways. The translator picked, "I like my cat" once, and "I love my cat." I like my cat 7 times, and I love my cat 3 times. So then, the probability of translating "Je mis mon chat" as "I like my cat" is 70%. So here in this little children's book example, we would pick "I like my cat" as the translation. So this is for a small amount of data, and I'm going to sort of go through these vast necessary math, a little bit of math. It's not really that hard, it's just more notation. So P of E is the a priori probability, and if E is the English string, "I like pizza," then P of E is the chance that a certain person at a given time will say, "I like pizza," as opposed to saying something else like, "I like ice cream," or "thank you," or any other thing. So you might think, how do you find this? We'll talk about that a little later, but one way that you can approximate it is something like the web. If we have all the documents on the web in English, we can say that people maybe often say, "I like pizza," and not so often say, "I like Brussels sprouts," or "I love George Bush," or other great things like that. So you can, if you have the total number of things that are said, then you can sort of derive a probability from that. Now, P of the foreign sentence given the English sentence is the conditional probability. So if E is the English string, I like pizza, and if F is the German string, danke, then P of F given E is the chance that upon seeing E, if you see I like pizza in English, you will translate that as danke. So you would be, that should be pretty low unless you're a very, very poor English student. So, but for something like I like pizza, however that correctly translates in German, that probability should hopefully be high. So this is the joint probability, and this is something you might be familiar with if these two items, the English sentence and the foreign sentence, have no connection, then we can just separate them out and multiply them. If you've ever done basic probability, if you're dealing with dice rolls or something where one roll shouldn't affect the other unless you're at a rigged casino, then you can actually separate these out. If these do influence each other, then we have to separate them like this. This means that the chance that E happens times the chance that if E happens, then F happens. So if they are mutual translation, then there's definitely some influence. So this is the way that we're going to separate it out in machine translation. Hopefully, your translation should be affected by the actual thing you're translating, else you're just a random string generator, which isn't a good thing to be. I've done that before, talks sometimes. Hopefully not today. Okay, so I'm going to go back to that slide. Maybe this will make a little bit more sense to you now that you know some of the notation. So given the foreign sentence, we're trying to find the English sentence that maximizes this probability. So then we have the correct translation of the sentence. So there are a couple problems. One is sparse data. Some strings don't exist in our data. I like gooblety gockety blah probably doesn't exist, but if gooblety gockety blah was something that was a new product by Coca-Cola, then maybe we should be able to parse that. So even though that makes a little sense, it doesn't exist in our data, so it would get a 0 probability. The best workaround here is to break the whole sentence into subcomponents and get counts on these and then recombine in sort of a clever rule. And really the best way to break it up is by using Bayes' rule. We have that probability of the English sentence given the foreign sentence. We can break this up using Bayes' rule, which is a basic rule of probability, and then we can find each of these and then derive that. So we can rewrite this expression as this. And this is the IBM noisy channel model, which I promised I'd tell you guys what it was. It sounds a little complicated. But why is it called the noisy channel model? Well, we imagine, this is a little silly, we imagine that someone has the English sentence in their head, but by the time it gets onto the printed page, it is corrupted by noise and becomes the foreign sentence. So French is just noisy English in this model, or German is just noisy English. So watch out for that noise in the air. That's why I can't understand what people are saying. So why do this? This enables us to separate out into smaller subcomponents. And the noisy channel model is used for lots of engineering problems. This was used for some, initially in speech recognition, some items would get garbled by actual noise in the atmosphere, and researchers in language decided, wow, if we apply this to machine translation, while it's not quite as intuitive, it works. So, and it's used for lots of other problems, signal processing, stuff like that. So there was a lot of mathematical rigor already behind it. So to bootstrap on that model was pretty easy and actually developed some pretty awesome systems right out of the box. As described by the IBM team, the translation model ensures that the words of E express the ideas of F, so the words of English express the idea of the foreign language, which you're translating from, and the language model ensures that English is a grammatical sentence. So you want to produce in a grammatical sentence as your translation, but also ensure that it expresses the idea, because we don't want to be random string generators. So I'm going to talk about language models. What's a language model? that's what I was talking about a little bit earlier with gathering data from the web. You can get fancy, but the easiest conceptually is to use a large monolingua corpus, for example, the web in English. You can count the occurrence of the English and divide by the total number of English sentences. The problem, again, is many grammatical and meaningful sentences won't exist in our corpus, so we're going to break the translations into the same parts and combine them. And if we combine them well, then we'll get a translation of high probability. So we're going to go, you could do this with words, but really it's best if you do it, you get a lot better output if you do it by phrases. And here what I mean by a phrase is not a linguistic phrase, but just a string of words. It's called phrases, again, because of some convention that propagated, and happy day for conventions. Okay, so here we go. Each phrase is translated into English, and then the phrases are reordered. So here we have, Morgen fliege ich nach Berlin zur Konferenz. Tomorrow I will fly to the conference in Berlin. So we translate and then reorder, and we have models for each of those. So here's a little visual for the phrase-based statistical machine translation. We have the parallel corpus, and from this we get two things. We get the translation model, which is this phrase table aligning sentences in the foreign language to sentences in the English language with probabilities. And from that, you can get that from the parallel corpus. You can also get the language model, if you want, by counting n-grams, which are strings, in your monolingual corpus. So you can get both of these from the parallel corpus, or perhaps use a larger corpus to derive the language model, because everything on the web isn't translated to other languages. So the actual punchline of this is the decoder, which combines the output of these two, multiplying the probabilities in the same distribution that we had before. And here it takes input, yo tengo hambre, and outputs, I am hungry, using the probabilities generated here. And the decoder is actually the open source component that I'm going to talk to you about next, called Moses. So here's just a little example of a translation table to give you a little bit of feel. The proposal, the idea, it translates a number of different ways, and you can derive this data. This was derived by the European Parliament data. So you can see it knows sort of what's going on. It's getting there, yeah. So here's the decoding part, and this is just obtaining the same probabilities and then finding the English sentence, which maximizes their product. This is called decoding, and we can't search through all the possible sentences because there are a lot of possible sentences. But we can look through a relevant subset of sentences, and that's where some of the cleverness of a good decoder comes in. By implementing a very good search algorithm and a good heuristic, you can actually do this without running forever, which is a good thing if you're working with an exponential NP-complete sort of thing. So the goal is to find a suitable translation. And we evaluate this with a certain type of metric. I'm not going to go into this in detail. There are a lot of automatic metrics to evaluate machine translation quality. And the importance of an automatic metric, there's still research going on in automatic metrics, but the importance of that is that you want to be able to evaluate your system and train it automatically without having to have a human in the loop all the time. So while a human is probably the best judge of translation quality, if you're going to use, in development, have your machine be happy when it gets a good score and sad when it gets a bad score, and train it that way, then you really need an automatic metric. I like to personify things sometimes in AI. So example, a system output, Parliament opens early. You might have a reference translation, Congress opens early, and it matches for certain substrings, and then you get a score based on that. So now I'm going to talk to you about the open source decoder Moses, which is a great thing. If you've ever tried to implement even a subset of a decoder, it's tough. There's a lot of issues with optimization, with reading in a lot of data, with search algorithms. And so what was going on with a lot of researchers in the field and in academia, in industry, they were reinventing the wheel, re-implementing these decoders because they were closed source, in general, very closed source. And so to gain an inlay into the field, you had to invest maybe 9 months, 1 or 2 people full time, just to get started. But that's no longer true, because now we have an open source decoder. So if you wanted to get into the field, if you wanted to make one subtle change, if you have a great idea, then you can start right away. Or if you just want to run machine translation algorithms without going through Google or with an obscure language pair, then you can actually do that for your own personal site or for sites of your clients. So Moses, an introduction, it allows researchers and hobbyists to avoid reinventing the wheel with machine translation. You can build a state-of-the-art, absolutely state-of-the-art, SMT, statistical machine translation system quickly, and add improvements to the source as desired. And it allows one to train translation models for arbitrary language pairs. All you need is a collection of translated text, parallel corpora. Of course, the larger these texts are, the better your translation quality is going to be. But if you want to experiment and see some funny things, you can try children's books, or maybe there's a Klingon Bible that's translated to Finnish or something like that. So you can really have some fun there. And it's an open source, lesser GPL license. The lesser GPL was, we wanted a GPL license, but the lesser was mainly because some companies nowadays, I guess, are scared of the GPL for their own little reasons. So the L just says, don't be scared of us, please use our software. Replacement and extension of Pharo, which was a very, very, very popular machine translation, closed source, developed at IBM. They wouldn't release the source code, so we basically re-implemented it from scratch over a year period. So it's a replacement as well as an extension of Pharo. And we've had a great response from researchers that used to use Pharo, from companies that used to use Pharo, now using Moses. So it has some highlights are a beam search algorithm, efficient search based on best first search, finding the highest probability translation among an exponential number of choices quickly. It's factored. This is a new climbing that sort of pyramid that I mentioned before. Words can have a factored representation, which means that we're not just laying at the bottom of the pyramid words to words. We're also going to try to climb it a little bit by representing words as vectors, including part of speech information, stems, which is shortening a word, and other linguistic information. So if you have data with that, you can actually now use more relevant linguistic information. And that's really an advance in the field. So it also interfaces with tools with ambiguous outputs, such as automatic speech recognizers, which if you're going to layer these components, if you're going to layer an automatic speech recognizer with a machine translation system, if they don't sort of deal with each other's ambiguity, then you'll end up with a really silly game of telephone, because there's going to be errors at the first level and errors at the next level. And by dealing with this ambiguous output, you can sort of begin to correct for those errors. So getting started, this is the practical part. Yes. So here you can just check out the Subversion repository on SourceForge. I don't know if you guys use CVS or SVN, but really great code managing system. So you just make a little directory, check it out. It uses but doesn't require a language modeling toolkit. It'll be in your best interest to download that, though, because it'll let you really run some demos out of the box. So then you want to compile it, and then explore and contribute. These are both important. So training details. The training process takes place in 7 steps, and I just give this for a little feel of how long this takes with a large amount of data. This isn't actually running the system yet, it's training it, so it runs much faster than this. But if you're going to train on the really, really large European Parliament corpus, you're going to have to budget a day. And if something goes wrong at one of these levels, then you have to start over. It's fun. So you want to start with a smaller corpus than the European Parliament, but if you really want a good system, then you're going to want to do this much data and invest a lot of time. So there are eight steps, and then once you're done with that, you have a trained system, and you can actually feed it. I'm going to talk about the feeding part. So we're going to feed it Das ist ein kleines Haus. This is the translation system that we just trained. And then we're going to look at the output. This is a small house. So the little toy model managed to translate the German sentence, which is a correct translation. So it's not correct in all cases, but it's getting there. And you can train this system yourself. You can do this yourself in a reasonable amount of time. So that's really awesome to me. And the decoder is controlled by this configuration file. So once you get it producing output, you can change some of the parameters and explore what really makes a good translation. And you can specify this in the file or in the command line. So if you have this little toy model working, then, and this is a toy model again, this is on the lower amount of data. You can train this up in 20 minutes or so, and it should run right out of the box. And so you can really play around with it and see what really influences statistical translation. So let's see. So that's the toy model that once you get Moses up and running, compiled, then you want to download this data to just do some tests and explore a little. So some initial projects that I've done that are sort of exciting is you can build a translation system using the parallel corpora of your choice. You can try the European Parliament data, or you can try some translations of the same novel or text, or your favorite user manual, maybe, even, which would output some funny translation. So just experiment with that, and note the influence of the size on the translation quality, or the domain. Well, it trains on any domain. If you train it on a very specific domain, then you're going to end up with translations specific to that domain. So next steps, I'm going to put these slides online so you can sort of check these out as you explore. But try some different things, lowercase the source and the target, adjust the hyperparameters, add a dictionary. You would think that would be automatic, but even a bilingual dictionary can give a few score points, and add some new features to the phrase table. So here are some resources. These are lots of sources of parallel data, or you can just think on your own, instruction manuals, War and Peace, whatever. And here are some software resources, most importantly, Moses, which I'm talking about. But there's also a scoring tool for machine translation evaluation, and Giza++, which is a training tool for some of the basis of the theory behind Moses. Mainly, Moses uses it to align words so that it can actually discover from the parallel corpora the phrases that should align to each other. So Giza++ contains algorithms that actually align those phrases. So here are some references, and I'm going to close with that. So today we went over some of the history of machine translation, different approaches to it, but really concentrated on the theory and practice behind statistical machine translation. And I gave you a little introduction to Moses, which is an open source decoder incorporating all the theory and practice of state-of-the-art statistical machine translation in the field, and you should be able to just go to SourceForge, check that module out, run the demo, and play around with it, and even do some silly things. I've seen some silly translation engines on the web, maybe translating from, I don't know, rap speak to English or stuff like that. You can do that on your own if you want to make a little silly toy system like that, or you can do something more serious, like really improve translation quality by maybe implementing a new heuristic or something like that. So I'd like to thank you, and if there are any questions, feel free to ask me, and I'll either answer them or direct you to someone who can better answer your questions. Thanks.
So with the factorial stuff, does that handle context sensitivity? Do you just break it down into linguistic units by sentence? Or if I use a phrase in an improbable way in one sentence, does that affect the translation? If I use it again in the next sentence, it's likely to be the same thing, or do you not parse on that level?
It depends on the data that you're using. If you're using factored translation data, if you use it in an improbable manner, the probability there is going to be very, very low. But if you have very good evaluation metrics, if you're evaluating things very well, it will notice if a subset of your translations are scoring very poorly. So it does incorporate that information, but in more of a statistical manner. So if you're using it in a brand new way, no one's ever used I'm verbing your noun in your fridge, whatever. If you're using I'm in your fridge eating your foods, if you've seen that internet meme. If you're using a verb as a noun and it's never been used that way before, then your translation is still going to be improbable. But it's improbable in our minds, I think, linguistically as well. And that's why the word has multiple components. You're not just basing your translation on the part of speech, you're also basing on the source form. So now that I'm in your fridge eating your foods or whatever is very common on the internet, then if you're using that as your data source, then you will start to improve your translation quality. Thank you.
Hi, so I'm just thinking about the problem that some things are expressed in a different way in different languages and phrases don't actually have the same structure.
Yes.
So you used the example of I'm hungry in Spanish.
Yeah.
And in Spanish, as in German and as in some other Romance languages also, it's to have hunger.
Yes.
In English, we have to be hungry.
Yes.
In some languages like Latin, there's a verb to be hungry as opposed to have or to be.
Yeah.
So those don't have the same structure. So I'm wondering, you could say they have the same structure in some sense. I'm wondering what you would need in Corpora in order to be able to correctly translate that for a wide variety of persons or tenses or whatever.
You just need a lot of data. So to begin with, it's pretty easy if you're not using a very inflected language. If there's just two forms of the verb, then you've probably seen all forms of the phrase, I am hungry, you are hungry, we are hungry. If it's a very inflected language, and we actually did research with Moses in a very inflected language, Czech, where it has a lot of different forms of the verb, just adding more data improves translation quality directly, and incorporating information about the part of speech, representing language as a vector instead of just trying to translate one phrase to another. So you can, in Spanish, yo tengo hambre, I am hungry. You see those in a parallel corpora aligned often together, so you can do that very easily. If there are 20 forms of the verb to have in Spanish, then that's where you would run in a little problem with that naive method. But that's why Moses is now incorporating information about the part of speech. So if you know that if it's a first person singular, it often translates one way, and if it's a second person plural, it translates another, then you can now incorporate that information.
So you could potentially go from, even if you haven't seen it in the third person, you could potentially go from hat hunger to he is hungry.
Yes,
even if you
exactly.
Haven't seen it in
with the factor-based model, not with the previous state-of-the-art, which was not using factors. It could only do that if it had seen it before. But with factors, you can generalize. You can say, often when I see it this way, it adds on an OS at the end or something like that. So that's one of the novel improvements that Moses offers.
Cool, thanks.
Not all corpora are publicly available, but the ones I linked are. And particularly the European Parliament data is publicly available. And that'll cover you for a lot of European languages. So I listed a lot of data sources, but there are a number of corpora that are very, very large and suitable for machine translation applications publicly available.
I'm sorry. I have a question. Is Moses playing dice? Is he like taking the probabilities as they come, or is he always taking the highest, the translation with the highest probability?
It depends what's actually going on in the inside, and I didn't go into a lot of these details because it's a little bit technical. You can check out the source code. But it ranks, it forms a lot of different hypotheses as to the best translation. And it does that by translating one phrase at a time, and it has a special stack of these hypotheses, and it ranks them as it adds on a new component, and then it picks the n best. So you can set n to be whatever. You could pick the top 5, the top 4. So that sort of it doesn't have as much of a random component as using the limiting. You don't want to. It's an exponential number of hypotheses, so you want to have a heuristic, and that heuristic might incorporate a bit of chance. A simple heuristic might be randomly pick a word and then only do this for 5 words and then pick the best. That would be a very stupid but simple heuristic. But essentially, it gradually forms the translation and can pick the best as you go. And at the very end, it can actually output, instead of one translation, you can have it output its top 20 picks. And you can sort of see, get an indication of how it's pruning out, how it's getting rid of some translations there.
Is 74 series glue logic? There's no...
I think I'm going to take one more question because I'm a little thirsty. 2 more? Okay, I can do 2 more.
How do you handle faults like wrong spelling, wrong grammar, and so on?
Lots of data. So if you have a lot of data, most people are going to spell things correctly. That's why there is a correct spelling even. So if you have a lot of data, then the correct spelling will just win out. If you have a small corpus and you misspelled something simple like cat, then cat is always going to be misspelled in your translation. But really a lot of data corrects for that.
And can it handle wrong input data too for a translation? If the input data is wrong, how do you correct it? So
that's one of the parameters that you can play with. Out of the box, it just takes the input as is. So if you misspell something, then you're probably not going to get a very good translation. But it's pretty simple to add something into the script that automatically spell checks, that gets rid of certain words, suggests spellings, stuff like that.
Where do you see the limits of this system? How do you handle different concepts like having a dual in a language as opposed to singular and plural? Or another other example, what would you do in Hungarian with the wife of a king as opposed to a queen? Or what do you do with 7 expressions for snow?
So there are, in fact, fewer expressions for snow than we thought before, but in some languages there are a lot of different expressions for one. Again, data seems to be the answer, but there are limitations to this system. And really, I think the next level that machine translation is going to take is going to be incorporating statistics with some of the previous rule-based systems and kind of joining them into a new hybrid model.
I think it was last year when the Logos system has been released to the GPL license, and it's now called Open Logos. I think it's a rule-based system that has been established and built up during the last 30 years. Do you know if there have been already attempts to combine these systems?
Yes, there have. I can't reference those directly, but a simple way, one of my colleagues at MIT right now is that little pyramid I showed you before. She's using the output of Moses and then doing some tree syntactic transformations that are slightly rule-based, using automatically generated rules as well as human rules, and then further improving the translation quality. But that's really on the bleeding edge, so exciting things are to come, certainly. So I'd like to thank you guys today, and I look forward to the rest of the CCC, and again, thanks for putting up with the technical problems at the beginning. So.